Well, welcome, ladies and gentlemen, to a new video. Today, we're going to continue to dive into Unit 1 by focusing on pure substances and mixtures. So hopefully by the end of today, you'll be able to differentiate between a pure substance and a mixture, be able to calculate things like empirical formula, and understand how the change of percent by mass can tell you a lot about what impurity might be in your substance. So let's go ahead and dive in. By the end of this video, you should be able to differentiate between pure substances and mixtures, calculate and solve for empirical formulas, calculate mole fraction of an element in a compound, evaluate experimental factors for determining the moles of a water in a hydrate, and determine the percent purity of a substance with an impurity. Let's dive in. So first off, let's start by differentiating between pure substances and mixtures. Pure substances are those that consist of just one element or a compound. So element would be just any single element on the periodic table, and a compound would be a combination of two of those elements that are chemically bonded to each other. Mixtures consist of two or more substances, but are not chemically bonded together. So things like salt water, sugar water, oil and water, all of those would be considered mixtures because they do contain two or more substances, but they are not chemically bonded together. Pure substances that are compounds are chemically bonded together. So those are the key differences between identifying between pure substances and mixtures. Let's talk a little bit about the law of definite proportions because that tells us a lot of information about how atoms bond and how we can go through and determine percentages of compounds. The law of definite proportions simply states that the ratio of the masses of elements of a pure sample are always going to be the same. What that means is that, for example, in methane, there will always be roughly 75% carbon and 25% hydrogen by mass. The molar mass of the entire compound of CH4 is 16, whereas the molar mass of carbon is 12. So 12 divided by 16 is 0.75, so roughly 75%. And hydrogen, there would be 4 hydrogens, so that's roughly a molar mass of 4 divided by 16, that's 25%. So all CH4 has that percentage by mass. And that's really important because then we can utilize that information and those percentages to work backwards to calculate empirical formulas, that is the lowest whole number ratio formulas of chemical compounds. So essentially we can use percentages and work backwards to figure out what our empirical formula is. Speaking of empirical formula, it is the lowest whole number ratio of atoms of the elements of a compound. Now, the molecular formula is the formula itself, the actual formula. The empirical formula is going to be in the lowest whole number ratio, so it may end up being different than your molecular formula. For example, on the right here, we have P4O10 as the molecular formula. Well, that is not in the lowest whole number ratio because 4 and 10 can be divided by 2 to give us P2O5. So that would be the empirical formula of it. H2O, you can't reduce that anymore. So the molecular formula and the empirical formula are going to be the same. You can see other examples there on the right-hand side. The real focus here, though, is being able to calculate that empirical formula. So what are the steps on how to do that? Well, let's take a look. So there are several different steps you're going to want to do as you go through empirical formula calculations. Number one, you're going to want to assume your percentages are grams, or if it just gives you grams, use them. So if you aren't given grams and you're given percentages, just assume those percentages are grams. Step two is we're going to convert to moles, which you can see there. We're given carbon, hydrogen, nitrogen, and oxygen. We use the molar masses of each of those. Notice that with things like hydrogen, nitrogen, and oxygen, they're not in their diatomic form, so we're going to use just 1.01, 14, 16, etc. We divide those and get those numbers into moles. We're then going to divide those moles by the smallest mole number. So out of those 4 mole numbers we get on the right-hand side, which of those is the smallest? We're then going to divide each individual moles by that particular mole number. And what we get at the end should be our empirical formula. We get 7, roughly 9, 1, and 2.5. Now, numbers may be close to whole numbers. So, for example, if you get something like in the example here, 8.97, that can be easily rounded to 9. But if you get something that's 0.75, 0.50, 0.25, even 0.33, you cannot round those numbers. They're not close enough to the whole number in order to be able to round. Keep in mind the more significant figures you use as you go through and solve these problems, the more likely you are to get accurate whole number ratios. But notice at the end there with our oxygen, when we divide, we get 2.5. If we don't get whole numbers, we have to determine what to multiply all the numbers by to get whole numbers. So 7, 9, 1, and 2.5. Well, that 2.5 one is the one that's kind of throwing us off there. But we know that the lowest whole number we can multiply 2.5 by to get a whole number would be 2. So in order to finish out the problem, we need to multiply all of our ending numbers by 2. And so what we get is 14, 18, 2, and 5, and therefore our formula is going to be C14, H18, N2, and O5, because those numbers at the very end become our subscripts for our empirical formula. Let's go ahead and do one more practice problem, again, together, and see how well you understand this concept. So let's calculate the empirical formula for lucite, also known as plexiglass. If you're a hockey fan, you know all about that. It's people smashing each other into the boards. We got 59.9% carbon, 8.06% hydrogen, and 32.0% oxygen. So step number 1 is to assume that our percentages are grams. So we're going to go ahead and do that. Is we're going to give our percentages, we're just going to convert them to grams. Step 2 is convert grams to moles. So we use the molar mass on the periodic table. Again, no diatoms here. So we get 4.99 moles of C, 7.98 moles of H, and 2 moles of oxygen. We're going to then divide by the smallest number of moles. So we divide each of those by 2 because that's our smallest mole number. We get 2.5, 4, and 1. Well, if we don't get a whole number, we need to figure out what whole number we need to multiply to get these to be whole numbers. Well, 4 and 1 aren't that big of a deal, but 2.5 is the one that's throwing us off there. So what we need to do is we need to multiply all of our numbers here by 2. That is going to give us 5, 8, and 2. Those then become our subscripts, and we get our empirical formula from that. So again, just following these simple steps will make it very easy for you to find any empirical formula calculations that you need to figure out. Hopefully that makes sense. Let's move on. So empirical formula calculations can be known to determine the unknown moles of water in a hydrate compound. Now, as you may guess, a hydrate compound contains water. So for example, in the top right here, we have copper sulfate hydrate, and we have copper sulfate there, and some number of molecules of water. In this case, it is unknown. Well, what we would do in lab is we would take the copper sulfate and we would put it, we would measure the mass of it, and then we would put it in a crucible. And a crucible is just basically a little porcelain container that has a lid, and we would put it under a Bunsen burner and we would heat it. And as we heat the crucible, the water then evaporates from the copper sulfate because it has a lower boiling point than copper sulfate does. Copper sulfate's ionically bonded and has a high boiling point. Water boils around 100 degrees Celsius depending on your altitude and whatnot. But we boil that off, and then what we do when we're done is that we mass it again. And once we do that, we have the mass of pure copper sulfate. We can subtract the difference and get the mass of the water that is lost, and then we can use those as our starting gram numbers and basically do the same thing, do an empirical formula calculation, except for one of them we're going to just use CuSO4, not the individual components of the compound, but CuSO4 itself, and water itself. And then over time, what we do as we get through that calculation is we would find out what number goes in front of water. So we can use these empirical formula calculations in a very similar way to determine the moles of water in a hydrate compound. I'm sure you'll encounter a lab where you have to go through and complete this process if you haven't already. The last thing I want to talk a little bit about is the purity of a mixture. And we can do some mixture analysis to determine if a substance is pure or not. Now, this is really important, so make sure you kind of listen in here. If an impure sample has a lower percentage of mass than the pure sample, so let's say that we have a sample that's 75% carbon, and then the sample that we're looking at is impure and says it's 60% carbon, so that tells us that the impure sample has a lower percentage by mass than the pure sample, then the impurity must have a lower percentage by mass than the sample. It's kind of the concept of grades. Let's say you've got a grade that's 75% and all of a sudden your grade drops to a 60. Well, you know whatever caused that grade to drop to a 60 has to be lower than 75%. Probably has to be even lower than 60%. So we can utilize that information to figure out what might be causing an impurity, or what impurity specifically might be in our mixture. Keep in mind that we can determine the percentage of a material in a sample by dividing the reported percents by the actual percent. Basically, it's your percent yield calculation. Take the actual over the theoretical and you get your percentage of material in a sample. So let's look at a sample problem here. We have KF has a percent by mass of F of 33%. What could be the impurity if the percent by mass calculated to be 40%? So we've got LIF, RBF, CSF, and FRF. So what we have is a percent by mass where the impurity caused the percent mass to be higher than what it should be. So in this case, we want to look for which of the following four formulas gives us a higher percentage of F by mass. That means that whatever F is bonded to has to have a relatively low molar mass, because that's going to give F a higher percentage of the mass in the compound. So the best answer here is going to be lithium fluoride. Lithium fluoride has a higher mass percent of F. In order to have a mass percent that is higher, the impurity must have a mass percent that is higher than the original sample. RBF, CSF, and FRF all have a lower percentage of fluorine because rubidium, cesium, and francium all have higher molar masses, which results in the percentage by mass of fluorine to be lower than what it should be. LIF, if it's the impurity, is going to make that mass percent higher. So it's a little bit complex to think about, but as you go through and reflect on it and think about what results in a higher mass percent, what results in a lower mass percent, you can easily figure out what the impurity of a substance is in a mixture. So hopefully today we've met all of our student learning objectives, except for calculating mole fraction from an element of a compound. I'll worry about that later. The point is, hopefully you have a really good, strong background on identifying pure substances and mixtures, being able to calculate empirical formula, and then lastly, be able to determine percent purity of a substance with an impurity. JLand Bio, hope you have a great day, and we will see you soon. Bye-bye.